Welcome to all of my students. Today I will deliver lecture number 19. In today's lecture I will try to finish unit 2. So in last lecture I discussed the definition of semi-modular lattice and one result regarding semi-modular lattice. In the last lecture I proved that every modular lattice is a semi-modular. Now I will prove that the lattice of equivalences on a set X is semi-modular lattice. So result number proposition 1.8.6. The lattice of equivalences on a set X is semi-modular. So basically this is the lattice of equivalences, correct? So we have to prove that the lattice of equivalences of a set X is semi-modular lattice, correct? We have to prove. Just I recall what is semi-lattice, what is semi-modular lattice. See, if you recall that if L is the lattice, this is the partial order relation, this is this is meet, this is join, this is the lattice. We say that when we say that it is semi-modular lattice, when you see when X cover X when A covers A meet B and B covers A meet B, then what does it implies? It must implies that A join B covers A and A join B covers B, correct? For every AB belongs to L. This should be for every AB belongs to L. So if for every AB belongs to L, A covers A meet B, B covers A meet B implies A join B covers A join B covers B, then it means that L is semi-modular. Correct. So see, so basically and what is the meaning of cover? That is, you say that A covers B, that is, when we say A covers B, there does not exist X belonging to L such that situation arises like this. So this is the definition of the cover, isn't it? We say that A covers B if there does not exist X belongs to L such that A greater than X greater than B, correct? And this is the definition of semi-modular lattice. Now we have to prove. Now see, here the elements are what? Equivalences will be the element, because this is the lattice of equivalences, correct? So proof, take any rho comma sigma belongs to the lattice such that rho covers rho intersection sigma, and sigma covers rho intersection sigma, correct? So rho covers rho intersection sigma and sigma covers rho intersection sigma. What we have to show? We have to show that what is our claim? Claim is that rho join sigma covers rho as well as sigma, isn't it? This is our claim. But what we do, basically these are the equivalences. We will show that if we instead of showing rho join sigma covers rho as well as sigma, if we show that the equivalences classes, we show it for equivalence classes, because equivalences classes are as good as equivalence relation, isn't it? That is, suppose A1, A2, A3, A4 dot so on be the rho intersection sigma classes. So what we will show, these are the rho intersection sigma classes, correct? So we show that these are the rho intersection sigma classes, correct? Now we think about what could be the rho class, what could be the sigma class, correct? And after that we show that the equivalence join of equivalences classes, is it clear? Join of equivalences classes covers the rho classes as well as sigma classes. Here it is written as relations, equivalences, isn't it? And we are talking about classes. So see, just I am again telling that equivalences classes are as good as equivalence relation, isn't it? If we show the thing for equivalences classes, then it also holds for equivalence relation. If we show the things for equivalence relations, then it is also hold for equivalence classes, because equivalence classes are obtained from the equivalence relation, isn't it? So suppose A1, A2, A3, A4 be the rho intersection sigma classes, then as rho join rho intersection sigma, so there is exact one rho class which is the union of rho intersection sigma classes. There is exact one rho class which is the union of rho intersection sigma classes, and two rows, and the row classes, and the remaining row class coincide with, and the remaining row classes coincides with rho intersection sigma classes. Sorry. So without loss, suppose that row classes are A1 union A2, A3, A4 dot so on. Now please understand how I have written row classes like this: A1 union A2, A3, A4. Why I have written that as row covers row union sigma, as row covers row intersection sigma. So there is exactly one row class which is the union of two row intersection sigma classes. Why? Why it is so? Why I have written it is the union of two row intersection sigma classes? Why not three? Think about this, isn't it? This is a fact. Think about this. Why? For example, if you assume that see, it's very obvious that row intersection sigma is contained in row, correct? So obviously classes will be contained in row intersection sigma classes will be contained in classes of row. It's obvious. But thing is that why it is written as exactly one row class is the union of two row classes. Why it is written this? Why not three? My question is that. For example, if you assume three, correct? If you assume three, then what happens? For example, A1 union A2 union A3 comma A4 dots on these. If you assume, for example, this will be the class, correct? If you assume row class is this is row class, and this is the row intersection sigma class A1 A2 A3 A4, correct? Now you can see in between there a class can come, say whatever you call it, say eta will come, which is what, A1 union A2 union comma A3 comma A4 dot so on. I forget that I have written, I think it is visible to all of you or not. Let me see. Oh, it's not visible. I am saying that if we take row as A1 union A2 union A3 comma A4 dot so on, correct? And row intersection sigma if we take A1 A2 A3 A4, correct? Then in between this some class will come, say A1 union A2 comma A3 comma A4 like this. So it will contradict that row covers. What does it implies? What does it implies? It implies that row does not cover row intersection sigma. As it is given row covers row intersection sigma, so there will be contradiction because in between eta will come between row and row intersection sigma, isn't it? So row must be like this. That is, it's one class must be, it's exactly one class must be the union of two classes of row intersection sigma, correct? That is why. Now same we can do for the sigma, isn't it? But as sigma is different from row, we have to take like this A1 comma A2 union A3 comma A4 like that. So similarly, I write this here. Similarly, the row covers row intersection sigma and row is not is equal to sigma. The two row intersection sigma classes that come together in sigma are not the same as that come together. So there are two possibilities. Either sigma classes are A1, A2, A3 union A4 dot so on, or we take class like this: A1, A2 union A3, A4, like this. Correct? Now we can see that in the first case, rho join sigma classes are A1 union A2, A3 union A4, A5 dot so on, while in the second case rho join sigma classes are A1 union A2 union A3 A4 A5, like so on. Now in each case it can be easily seen that rho join sigma covers rho and rho join sigma covers sigma. Hence proved. You see, either we take this possibility or this possibility. If you talk about this possibility, that is if sigma classes are like this, so we can see easily that A1 union A2, A3 union A4, A5, it will cover both rho as well as sigma. Isn't it? This is rho. It is covering here, because here it is A3, here A3 union A4. So it will cover this. Correct? Now if we talk about the second case, so A1 union A2 union A3 will cover this also. Of course, it will cover this also, isn't it? So in this way, in each case, rho join sigma classes covers rho as well as sigma, both cases. So in this way, we have proved that the lattice of equivalences is always semi-modular lattice. Correct? Now we see the next definition, that is the direct product of lattices, and how we define here partial order. lattices, then is a partial ordered set. If we define x1, x2, xn less than or equal to y1, y2, yn implies xi less than or equal to yi, and I runs from n to 1. Also, L is a lattice with and x1, x2, xn join y1, y2, yn.